So 2.9 and 2.10, or really all of the second part of Unit 2 deals pretty much with logarithms. I really like teaching logarithms. I think they're really interesting. I wish I could go into applications a little bit more than we do. But you have already learned about logarithms, but I usually find that students can't really answer this question: what is a logarithm? You learned how to do some things with them last year, but if we're talking about what in the world is a logarithm, I think that the way that this is presented in AP Precal really helps you sort of understand what a logarithm is and why we need to use them. So a logarithm can be defined as the power to which a number must be raised in order to get a certain value. So, for example, if I have 2 to the x power equals 16, that is not a logarithm. It's an exponential equation, right? But what value would I have to have there? What number would that have to be raised to? It would be 4 for that, right? So x would be 4 in that case. This could also be the base 2 logarithm, so log with a base 2 of 16. I think I have zoomed in somehow and made this right. This is right huge. Okay, that's better. Okay, so the base 2 logarithm of 16 is 4.
That's wrong, isn't it?
I think it can. I made them put about the point 6.51. Because if you rotate it 180 degrees around the middle of that figure, it works the same thing like right here. Because if you rotate it 90, it's going to be down here. But if you rotate it 90 around the center of that, so I made them put about a specific point for that.
Okay, not necessarily rotating about the origin. Right,
because if it's about the origin, both of those would be wrong, I'm pretty sure.
Yeah.
I mean, it's been like 7 or 8 years since I taught it, but yeah.
I know that, okay.
Yeah.
All right.
Yeah.
That's a great idea. I'm rotating about the origin like a good unit circle.
Yeah, yeah. We're teaching Miss Martin's class today for, she's sick and needed us to teach them how to do what they're doing. And I have not done math 2 in 7 or 8 years, so had to use the answer key. The answer key's not quite right. All right, so for this is log base 2 of 16. So the base of that log is the number that's being raised to that power, and then the number that you're taking the log of is what the answer to that exponential would be. Oh my. So if I have like 2 to the x equals 1024, right? That one's a little harder because the numbers are starting to get out of hand. But does anybody know what that one's going to be? It's 10. You're right. So that would be 10. So you could write that as the base 2 logarithm of 1024 would be 10. Okay. Logs have a lot of really cool uses. You know, obviously, like your parents are not using logarithms to balance their checkbooks or pay their bills or anything. This is not like it's something that people use in everyday life. But there's a lot of instances specifically in like science and data analysis sort of careers where logs are used heavily. So it's an idea that is used a lot in several different fields. You know, what are the chances that you're going to use logarithms in your future? It might be low. You'd have to be interested in some very specific fields. I think it is cool to know a little bit about things, even if it's not something I do every day. It helps you understand what's going on a little bit better. One in particular, or a couple in particular that we see that are logarithmic scales that you use would be the Richter scale. Although whenever I was looking this up a little bit more, I read that the Richter scale is actually not what we use for earthquakes anymore. It's an old scale that Mr. Richter came up with, and that they have modernized it, and the moment magnitude scale is what scientists are actually using these days. It's similar to the Richter scale, but it's updated a little bit more. However, if you ever hear people talk about earthquakes and how bad they are, they probably call it the Richter scale still for that. But Richter scale, I do not know the answer to that question. I did not do extensive research on this, but I'm going to say 60s, but that's a guess because I don't remember that article very well. So I'm not sure about that. The Richter scale or the moment magnitude scale, whichever one you're talking about, they work the same way. They're just a little bit different ways of calculating. So many of you, like myself, might be a survivor of the Sparta earthquake. Do you guys remember that one several years ago? That shook a little bit here. So you too may be a survivor of that earthquake. I can't remember what that one was. Does anybody remember? It's like 4 maybe? Maybe it might have been like a 5 if you were in Sparta. Maybe it was a 5. Maybe it was close to 5. I can't remember. But let's call it a 4. So if you were a survivor of that 4 earthquake that shook Sparta, and we could feel a little bit down here, then you have a little bit of an idea of what that felt like. If you were asleep or if you were up doing something and not paying attention, you probably didn't even know it happened, right? It might have knocked over a picture frame or something in somebody's house, but it did not do much. But the way that the Richter scale works, or the moment magnitude scale works, is that it's a logarithmic scale. And in a logarithmic scale, each time you increase by 1, it's not like you're just adding an intensity of 1. You are multiplying by 10. So if we have a 4, which many of us have experienced, if we experienced a 5, it would be 10 times worse. Right? So a 5 would be 10 times worse than the 4 there. So then if you have a 6, right, that would be 10 times worse than the 5. How many times worse is a 6 than the 4? It'd be a lot. It'd be 100 because you're multiplying by 10 twice. So like if we start getting up 7s, like it's in the news when you're in the 7s, right? If you start getting up in the 7s, how many times worse is a 7 than our Sparta earthquake if it was a 4? That's 1,000 times worse. So if we called ourselves survivors of the Sparta earthquake, those who have survived a 7 might feel a little offended by our claim that we've survived an earthquake, right? Because it was pretty much nothing here. But a 7 is going to cause significant damage and be, much more risky. So that's a logarithmic scale. Another scale that works that same way is the decibel scale. I think we had a question just recently that was like a decibel problem. In the decibel scale, I believe the decibels is like 20, 30, 40, 50 is sort of where your benchmarks for that. It doesn't go up like 1, 2, 3, 4, 5. But from 20 to 30 is 10 times worse. Not because you're adding 10, but you're multiplying by 10. Obviously, you're not multiplying the number by 10, but you're multiplying the intensity by 10. So like if you have a sound that is a level of 30, and you go up to a 40, it is 10 times worse. But if you go up to a 50, it is 10 times louder. So whenever you start getting into ranges that are harmful to your hearing, you might just go from like 90 to 100, but it's 10 times worse. If you go from 90 to 110, it is 100 times worse. So it starts to be where each little increment is going to damage your hearing more and more. For that. I don't know if any of you have Apple Watches, if you've ever cut the sound thing on where it'll alert you when you're in loud environments. You can try it sometime if you've got one. Because I cut it on because my husband likes to play the guitar way, way, way too loud. And I was trying to prove to him that if he continues to do that, he is going to not be able to hear a thing whenever he is an old man. But it has not worked. But I would just like stand in the room and my watch would go off because it's too loud. It also alerted me one day, one of the kids, this has been a little while back, Henry had a birthday party at the indoor pool at the Fairfield Inn. Y'all ever had to go to, take a little brother or sister to the indoor pool party at the Fairfield Inn? Your watch is going to go off on that one. It's so loud. So those are, instances that we're probably kind of familiar with that they apply to. It's also going to be any time that you have data analysis where you're dealing with really, really large numbers. Another time that I first saw this was back during like COVID times whenever they were really tracking those numbers. One of the websites that I would check pretty often because I was, as a math teacher, I was kind of fascinated with the level to which we kept up with data on that. And it was kind of, interesting to look at what's happening with the numbers. Like one of those websites that I used, you could see like the regular graph, but that website had an option to change it to a logarithmic scale on that graph. Because what was happening is like those numbers sort of skyrocketed. So when you looked at a graph, it looked just like flat line and like this. Like you couldn't really tell what was happening in any pattern because the numbers had gotten so big that the numbers at the beginning seemed very, very, very small. So it was something that was interesting to look at. Anytime you're dealing with really large numbers, logarithms can come in handy. So I would love for us to spend more time on like applications. We'll do a little bit as we go along, but there's not a ton of it in here. Know though, certainly if you went further with math, if you went into like data analysis as a field, you would definitely run into this a lot more. So inverses. The logarithm is the inverse of an exponential. Okay, exponentials and logs are inverses. This, for me, is the best way to think about logarithms. Logarithm is how we undo an exponential. If we think about that first slide that we did, you could see that there was that relationship. So whenever you learned logs, you probably learned them using these formulas right here. So if we have an exponential form of b to the a power equals c, it could be written as log base b of c equals a. And a lot of times in Math 3, kids kind of learn this almost like a puzzle. So b is your base on your exponential. It's also going to be your base of your logarithm. We might want to write that down. This is called the base. Okay. And then a is the exponent over here, but it's the answer over here. C is the answer over here. It's what you're taking the log of on this side. So most of the time when kids come to me, they do these problems like it's a puzzle. Like my base goes to this piece over here, then my A goes right here, my C goes right here, and you just like rearrange that. It works perfectly fine. You are welcome to keep on doing that. When I teach this, I teach it along the lines of inverses a lot more. I think it is helpful when we get to the stuff that's a little bit harder to do it this way. So do it the way that I'm doing it if you want, or stick with your sort of like puzzle method there. But either one of them will give you the right answer. Let me show you what I'm talking about actually, let me do one more thing first. Then I'll show you what I'm talking about. So it is important to note that log base b of b equals 1. And b to the log base b of 1 equals 1. Okay? What this is telling you, essentially, is that when I do log base b of b, those cancel each other out. They're inverses of each other. I should have written this with like an exponent of 1 right there. That's my exponent right there. So the log base b of b cancels out, and the exponent is the only thing that's left. Or if I have a base raised to a log that has that same base, we're doing an exponential of a log with that same base. These cancel out, and I get it just whatever value is there. So if I'm asked to do log base 4 of 4, that's 1. They just cancel each other out. The exponent right there is the only thing left, so it's just 1. Or if I had log base 7 of 7, or log base 10 of 10. Anytime my base and what I'm taking the log of match, then they just cancel each other out. 2, similar but a little bit different. I've got 2 raised to the log base 2 power. Having a 2 raised to a log base 2 power, those are inverses of each other, so they undo each other and they cancel out. Now, in this case, it's not going to be 1 because I'm doing this of 5, so I would have the 5 there left. So seeing example 2, what would happen with 3? What would my answer for 3 be? It is going to be x plus 5 because the 3 and the log base 3 are going to cancel each other out. I like to teach everything to do with logs and exponentials based on this idea right here. That's the way I like to think about it. But let me show you both ways so you can see sort of like what you have learned before and how it relates to what we're doing now. So if I've got b to the a equals c, this is just from the other one, log base b of c equals a, right here. So if I'm trying to rewrite example 4 as a logarithm, then I could just use what I'm going to call the puzzle method, where we like put our pieces where they go, right? So 5 is my base, so that goes right there for the b. So I've got log base 5, right? Hey, Lexi. Yes. Probably just doing that again in class. Yep, let's take that. So that worksheet will be like the homework. It's not going to be due until Monday, because tomorrow we're just doing the worksheet. All right. So we got log base 5, and then the exponent goes over here on the other side of the equal sign. The answer of the original goes over here for that 25. You might see that 25 with parentheses or without parentheses. It can be written either way. Make sure you're writing that base on that log as a subscript. So it's little and it's below. Okay. Now, the way I like to think about these, and honestly you don't have to write anything down when you do these problems, is this. So I'm going to write it over here so I can explain what I'm thinking by writing it down. Now, normally I do this all in my head. I don't write anything but the answer down. But if I have an exponential and I want to rewrite it where it's logs instead of exponentials, I need to get rid of that base right there. I need to get rid of that 8. And I can do that by doing log base 8 of this side. But if I do log base 8 of one side, what do I have to do to the other? Also, log base 8, right? Those are the basic rules of algebra, that if you do something to one side, you've got to do it to the other. So I would also do log base 8 of 512. I'm going to even write this out. And I would never write all this, but I want to be very clear in what I'm thinking about. Here. So I've got log base 8 of 3. Log base 8 of 8 to the third equals log base 8 of 512. Well, log base 8 of 8, that just cancels out right there. So I get 3 equals log base 8 of 512, which will be my answer over here. Now, if you do it this way, if you're thinking of it this way, your answer will probably be reversed from the way that you see me write it in 4, like the sides of the equal sign. But it doesn't matter because I could just rewrite this log base 8 of 512 equals 3 if I wanted to write. That's the same. You can just switch sides of the equal sign. Now, as I said, I do not normally write anything down for this. So if I'm doing number 6, what I think of is I got 6 to the x power equals 125. I never did attendance, or I would have noticed. But Luke is not here. So Luke, here are the notes. There. Alright, and so I've got my 6 as my base, so I could log base 6 on this side to cancel out that 6. And if I do that, I got to log base 6 of the other side. And so on that left side, I'm just left with x. On the right side, I've got log base 6 of 125 for that. And I'm going to pause this for a second because I just realized that I did not do it. Okay, questions so far? Alright, so in a similar fashion for like example 7, one way that works perfectly fine for this is to do sort of like what I've called the puzzle method, where you say, oh, 5 right here. What was that doing? 5 is my base. So 5 is going to be my base of my exponent. 4 right here would be like our A, so it's going to become the exponent right here, and that will equal 625. So you're just kind of identifying your pieces and putting them where they go. However, I prefer to think of it as an inverse. If I've got a log base 2, then the exponential is the inverse of that. Not raising something to the second power, but doing 2 raised to the log base 2 power. So I'm making this a power of 2. So 2 raised to the log base 2 is going to cancel out. And so if I do that, I must also do 2 to that power on the other side. Okay, so these cancel. I just have an 8 over here. And then over here, it's really important. This is 2 raised to the third power. Thank you. I also forgot to cut the recorder back. No, I did cut that back on. All right, so what I did right here, 2 raised to the log base 2 cancels out the log on this side. And so I'm doing 2 raised to the third power. I'm using that little like caret symbol. It's the symbol on the calculator that means raise something to a power. There to remind me, 2 is my base being raised to the third power. It would be wrong to say 3 to the second here. For 9, I see log base 7 of x equals 10. So if I do 7 raised to that power here, that cancels. And if I did 7 to the power on one side, I got to do 7 to the power on the other side. So x equals 7 to the 10th power. Okay, questions? All right. Okay, there are a few special logarithms that we have to know about. The first one is called the common log, and if you see log without a base at all, then it is assumed that it is a 10 for that. So if you see a log without a base at all, it's assumed that it's base of 10. It is interesting to me. AP Calculus seems to always put the 10 there, which I find odd because like every pre-calculus book or stuff that I've seen before, they pretty regularly use log x without putting a base on it for their log base 10. But it appears to me on the stuff I've seen AP put out that if they're going to use a log base 10, they write the 10. So I'm not sure why they do that. I don't know if it's like an international sort of thing, like there's some countries that maybe don't use the common log. So since that test is given in some different countries, they like just do it this way to make sure you know what you're talking about. I'm not sure. But if you see any problems where there's no base, it is a 10. The other one that you will see, and they will definitely do it this way on the AP exam, is natural log of x. Natural log of x is a log with a base of e. Okay, e is a number. It is 2.71828 something or another there. So you know it is sort of like pi, except for it's a different value. It's not a variable. It's a constant there. So yes, Euler's constant is its name. Yes. There. So E is the base for a natural log, right? And if you take calculus, these are about all we deal with as far as exponentials go. Whenever it comes to exponentials, we don't really even use other bases very much. So these problems work the exact same as the ones we were already doing. It's just you have to think a little bit harder because the base is not written for you. So if I look at number 10, there is no base on that logarithm. So what is the base? It is 10. Sometimes you might want to like actually scribble it in right there so you know that it's a base of 10. If I have to rewrite this in the opposite form, if I want to make this an exponential, how do I get rid of a log base 10? What? 10 to the log base 10. Right, I'm going to do 10 to that power. That will cancel out my log over here. I'll just be left with an x. I must also do log base 10. What am I doing? 10 to the power. 10 to the power over here. That is going to give me 10 to the third. Let me rewrite that because that is a mess. X equals 10 to the third. Which you'll see, we'll be doing this soon, actually solves that equation for you, right? That x equals 1,000 for that. Right now we're just rewriting that. So if I look at 11, what's the base on 11? E. It's not written, but there is an e there. So if I want to get rid of a log base e, I need to do e to the power. To cancel that out, that gives me 4 over here. I need to do e to the power over here. I will get e to the x power. So 4 is going to equal e to the x. What? No, there is no log for those. Because when you see natural log, that is a log. You're trying to get rid of the log to write it as an exponential. So if your original problem has a log in it and the instructions tell you to rewrite, you should not have a log in the answer for that. If your original problem does not have a log, if it's an exponential and they've asked you to write it as a log, then you should not have the exponents. You should only have a log in that rewritten. So like if we look at 12, this one is an exponential, right? There's no log anywhere there. So if I want to get rid of a base of e, what do I need to do to both sides? How do I get rid of bases for exponentials? I would use logs, right? So I'm going to do log base e. If I'm writing log base e. Log base e is fine. It is mathematically correct. It also makes it look like you don't really know what you're doing very well here. Because what is the other way we could refer to log base e? Natural log, right? So as you become more familiar with this, you're not probably going to write that. You're going to write natural log. But if you need to, write log base e right now to remember that that base matches. But whenever you see your answer, they're not going to call it log base e of 5, although that is mathematically correct. They are going to call it natural log of 5, which is equivalent. Okay, we good here? Questions? Natural log is going to be the inverse of any type of exponential that has an e. So like the place that we used, the e was like in our continuous growth, like the PE to the RT formula. So if you have anything dealing with that P times E to the RT formula, and you need to solve something about it where you may have to use that inverse, that's where that's going to come in for that. And we'll get to some of those, not today, but soon. That is a much longer explanation that I do not have time to go into. But Euler's constant is pretty fascinating and shows up in all kinds of crazy places that I don't have time to answer. Right. And honestly, like I'm not an expert on it, but I do know a few things about it. All right. Now, these next problems are going to ask us to evaluate logarithmic expressions, but we have to do it without a calculator. Okay, so if it were calculator active, we get to use Desmos this year. So there's something on the next page we may not even really hardly do, but we get to use Desmos this year. If it is calculator active, then you got two options for typing this in to the calculator. On Desmos, there is a special function for it. If you go to functions, you can go down here. Did I pass it? They put it under the calculus stuff for some reason. Log base 2 of 8, and it gives you the answer. Right? If you do log shift underscore, like you're going to type an underscore. Oh, why is it not working? Shift underscore. It'll take you down to the base. You can type a 2. And then go over, do 8, right? And type it in that way. This is very straightforward sometimes. You might have to do that. But we also have a lot of questions on our exam that are not calculator active. So there is a decent chance that they will give you one of these, and it will be on the calculator inactive section. So you will not have the option of typing it into the calculator. So there are two different ways that you can deal with this, and I'll show you both of them. So the first thing that you could do, and you kind of need to know both because they might take they might take either one of these approaches, and what they love to do sometimes on these questions is they don't give you the answer as your answer choice. They give you like a step. They say which one is equivalent, and then you have to know how to write it. So log base 2 of 8. One thing I can do is I can like just say that equals x or question mark or whatever variable you want to use there, and I can rewrite it as an exponential. So if I rewrite this as an exponential, to get rid of a log with a base of 2, I would do 2 raised to that power, and that will cancel over here. I'll just get an 8. And then over here, I also have to do 2 raised to that power, and I get 2 to the x. And then I can just guess and check to see what answer I get, because it should be a whole number answer. So what 2 raised to what power would give us 8? That is going to be 3. So log base 2 of 8 is just equal to 3, which we also saw when we typed into the calculator, right? So that's one way to approach it. Here's another way that I'm afraid they may, this is the one I'm afraid they may give you as far as like giving you a multiple choice question and the answers are not really the answers. The other option, if I've got a log base 2, if I had 2 to some power right here, then my log base 2 and my 2 would cancel, right? So 8 can be written as 2 to what power? 3, right? So I could rewrite log base 2 of 8 as log base 2 of 2 to the 3rd, and log base 2 of 2 cancels, and I'm just left with the 3 right there. So you have both of those options of dealing with this. So like if I want to do that second idea here, if I've got this log, what's the base on this log? It is 10 because it is not written. So I could do log, for the sake of clarity, I'm going to put that 10 right there. Log base 10 of 10 to some power, right there. Let's see, Rowan, 100 could be written as 10 to what power? Second, right there. So that would be a 2 right there. My log base 10 and 10 cancel. I just get 2 for that answer. Now, 15 and 16 are a little bit trickier. Let's stick with this second idea just because I think it's a little different and I'm afraid they're going to give it to you. So if I've got log base 16, I want this to be 16 to some power. 4 to what power would give me 16? Oh, I'm sorry. We got to do that backwards. I said that wrong. 16 to what power would give you 4? It is 1/2, right? That one's a little trickier because it's not a whole number right there. It's going to be 1/2 because 16 to the 1/2 is the same as doing what? What? Say that again. It kind of is. I would think of it as like a square root of 16, right? Because when we have those fractional exponents, that can be written as a root. The 2 goes on the outside, the 1 goes on the inside, and that would be 4. So if I write it this way, log base 16 of 16 cancels, I get 1/2. Okay, questions? Here, I've got log base 3, and I need it to be 3 raised to some power right here. Now, what? I did kind of just write it, because what is supposed to go there? 0. Right? Because the only way you can get 1 is if you raise something to the 0 power. So those cancel. I just get 0. Now, let's put ourselves a note here, because this is important. Log base b of 1 always equals 0. No matter what b is. Yeah, so the other way to think about this right here is to rewrite it as an exponential. So like 3 to the power here equals x. 3 to the power here. So 3 to what power equals 1. And that power that you're raising it to is 0. So it would be 0 for that. And that's going to be the case no matter what your base is, right? Because if we're getting 1, the only way we can get a number to turn into 1 using exponentials is if we raise it to the 0 power. For that. So if you do the log of 1, no matter what the base is, you're going to get 0 every time. Unless you have a base of 0, in which case it's just like undefined, but you won't run into that. Okay, questions? Okay, this is really a slide left from last year where I had to teach everybody how to do it on this calculator instead of being able to use Desmos. However, there might be a couple things they might ask us about later that we might see this. The change of base formula has its biggest use in early stages of logs in that it makes it easy to type something into this calculator. Because this calculator has a button that says LOG and it has a button that says LN. But it does not have a special button for like a log with a certain base. Even though if I don't think it does. I think I've updated all these and it doesn't do that. So you can get to it if you go to math. There's an option for log base and you can use it that way. But again, we don't use these very much and that's a lot of steps to remember where things are at. So an option for this that you don't necessarily have to use, but I'm going to show it to you. If I've got log base 3 of 5, I can write that as log 5 divided by log 3. Base goes on the bottom. And so That makes it where you can take this calculator and you can type log button 5, close the parentheses, divided by log button 3, close the parentheses, and it will give you the value right off. So I'm getting, when I do that, 1.46497, so there. However, we're allowed to use Desmo, so that's all the time I'm going to spend on that right there, because I want to get to the end of everything. Change of base may come up in some theory problems we're going to see later on properties, but we'll go back over it. 20 is not really a new question. 20. Which one of those tables shows an exponential pattern? Or f of x, g of x, or h of x? Which one of those is exponential? Okay, I'm hearing H. Do you guys agree?
Yeah.
Okay, that one is exponential. How do we know that one's exponential? And when you say they times by 2, what are you talking about? The y coordinates are multiplied by 2, right? It is not 1 or f because you're just increasing by 2. What is f? What type of function would it be? That is linear. Okay. What about g? What is that one? That one's quadratic. They didn't ask us that, but I go up by 1, I go up by 3, I go up by 5. If I do a second difference, I go up by 2 for both of those. So that one's quadratic for that one. We have already looked at identifying linear, quadratic, and exponential. We need to be able to identify logarithmic from a table as well. So, logarithmic is going to be a little bit, or kind of a lot different than the other ones we've seen. But if you think about the fact that a logarithm and an exponential are inverses of each other, it should kind of make sense what we're going to be looking for, right? Because if I have this table, which is the one from example 20, and that is exponential, if I want to write the table for the inverse, what do I need to do? Switch, right? So that would be 1, 2, 4, 8 right here, and 0, 1, 2, 3 over here. So in this table, our y's are being multiplied by a number. In our inverse table, our x's are being multiplied by a number, right? So I have a couple statements here. The first one is for exponential functions, and the second one is for logarithmic functions. So in an exponential function, the input values increase in equal intervals, and the output values increase proportionately. I think that E is supposed to be there. I might have spelled the whole thing wrong. Who knows? And that word proportionately means that we're multiplying by a number. So for a log, that's the inverse of an exponential. So our x and our y's kind of switch here. So in a log function, the input values increase proportionately. And the output values increase in equal intervals. So in a log function, we're looking to see the x's being multiplied by a number and the y's increasing by equal amounts. So let's look at what some of these look like. Okay, here's 4 tables, and we need to go through and tell whether each is logarithmic, exponential, or neither. If I look at this first one, what do you guys think? Okay, tell your neighbor what you think. Okay. All right, Hayden, what do you and Luke think? That is correct. Exponential. Okay? X values are increasing by 1. H values, what are H values being multiplied by? 1/2, right? So it's exponential decay in this case, but it's still exponential. Okay, look at the second one. Okay, tell your neighbor what you think about that one. Okay, Enrique, what do you guys think?
Logarithm.
That's right. And how could you tell, Enrique?
I don't know. Kind of.
feels like it's got to be the answer. In a logarithmic, we want the y's to increase by equal amounts, right? So what are you doing to get to the next number for your y's? You're adding 10. These are increasing at a constant rate, which would almost make you think it's linear, right? But we got to check what's happening with the y's. What is happening to get from 10 to 30 and then 30 to 90? What are you doing there? Multiplying by 3. So you're looking for the y's to increase by equal amounts at a constant rate. You're looking for the x's to be multiplied. Okay, everybody look at 23. What do you guys think on that? Okay, tell your neighbor what you think on that one. Okay, Mackenzie, what do you and Stephanie think about 23? I like it. That looks good. Okay, why did you say neither on that one? Both sides are being multiplied, right? I don't know if there is a special name for that or not. I'm not sure what type of function that is. But all we need to know right now is neither linear, logarithmic, nor exponential. Okay? And then the last one. Tell your friend what you think about that one. Okay. Rowan, what do you think on that one? That is a log. The y values are decreasing by 3. The x values are being multiplied by 2. Okay, questions? All right, let's look at finding inverses of log functions. Okay, so for finding inverses, you do the exact same thing that we did when we were finding inverses of other functions. The only difference is now we've got logs and exponentials we have to deal with while we're doing this. So when I have this f of x right here, it is like my y. What's the first step of finding an inverse? Switch x and y. So I'm going to put x equals log base 7 of y. And I'm trying to solve for that y. So if I'm trying to solve for the y, I'm trying to get rid of log base 7. How do I get rid of log base 7? 7 raised to that power. We'll cancel that out on the right side. And if I do that to one side, I also have to do it to the other. So I'm getting 7 to the x power equals y. They will probably rewrite that with inverse notation like this and get f inverse of x equals 7 to the x. Okay, the next one, this is a y. So we need to switch x and y. So we get x equals 3 to the y right there. So for this one, kids mess up on these a lot more than they do number 25. Because we need to get rid of that 3. How do you guys think we should get rid of the 3? We need to log base 3. What do you think kids do wrong? What do you think they might do that would not work? Anybody was thinking, somebody divide by 3. Lots of people try to divide by 3. We won't say who was thinking they should divide by 3, but there were probably several of you thinking maybe we should divide by 3. This is 3 to the y power. It is not 3 times y. So to get rid of a base, we'll do log base 3 of both sides. And so we'll have log base 3 of x equals y. That will usually be rewritten with, actually I should use a g right there, not a f. G inverse of x is going to equal log base 3 of x. Alright, 27 is going to get a lot crazier, right? We got double logs on this one. So the process, though, is still the same. Switch your x and y's. So you got x equals log base 2 of log base 5 of x. So you're trying to get that x by itself. You have to start furthest away from that x. So you need to start with that log base 2. How are you going to get rid of it? Not a log. It's going to be 2 raised to that power. Right? So to get rid of a log, you'd never use another log. It's going to be the exponential, where we do 2 to that power. So you just take that base raised to the power. So now I've got 2 to the x power equals log base 5 of x. Oh, I'm sorry, that should be the y. Right there, I've got 2 x's in this one. That should be the y. Right there. Okay, again, I'm trying to get to that y right there. How do I get rid of a log base 5? 5 to the power. So I've got to do 5 raised to that power. So what I'm getting is 5 to the 2 to the x. A power to a power to a power. Now, it is unlikely that they're going to leave. Oh, and I shouldn't be writing over here. I got another problem. I'm going to run out of room. I got 5 to the power to the power. It's unlikely they're going to leave the answer like this. But when I've got powers, 2 powers here, then I've got a couple options of how I could write this. And they might give you either one because this was also in our curriculum. So I can treat it like this, 5 to the 2nd to the x, which would give me 25 to the x power. Another way that they might write it is, what do I do with exponents if I'm doing powers to powers? Multiply them. So they also could write it like this, 5 to the 2x equals y. If it was a free response question, either of these would be fine. If it was multiple choice, they wouldn't put both answer choices there for that. That all goes with 27. I really... Technically, we should be restricting some domains here, but we'll talk about that later in another section right here. The last one would be x equals 10 to the 2x minus 1. Y minus 1. Switch your x and y's. You're trying to get to that exponent. To get to that exponent, you got to get rid of this 10 first. How do I get rid of that 10?
Log it.
Log it. No raising, because it's already raising to a power, right? So we got to log it. If you want, you can just do log, because this has a base of 10. It doesn't hurt to write log base 10, but you don't have to, because that is the common log. This will cancel. We'll get 2y minus 1. And then from here, you are just solving the rest of that equation, right? So, Zoe, what would we need to do next? Add 1. So we got log x plus 1 equals 2y. I'm going to put parentheses around that x just to be clear, like that 1 is not on the inside of the log.
Is the x is raised?
X is what you're taking the log of. If you want the base, it's a 10 right there.
So is the x raised?
No, it's like log of x right there. Is that what you're asking?
If I'm writing the x above the log.
Yeah, no, it's not raised. It's like if you're writing this, if we have a like lined paper, it's log. Like if you want to write the base 10, it's down here and it's little. The x is like in line with the log. The x, because a lot of times people will kind of like write x like it's an exponent. It is not. Sometimes they will put parentheses around that. Sometimes they will not. But it's in line with the log. That's probably a good question to ask there. So last step on this is you need to divide by 2. I'm way running out of room right here. But you're going to get y equals log x plus 1 over 2. Okay, questions there? Okay?
Did you go back?
Yep. Good. All right. Just to think about graphs a little bit, if I've been given the graph of k of x equals 2 to the x, and I want to sketch a graph of the inverse of x, which would be log base 2 of x, what would I need to do for that? I've already got a dotted line there. What do I need to do with that dotted line? I need to flip, right? So sometimes that is easy to see. Sometimes it is hard to see. The other thing you can remember is that you can switch the coordinates of your point. So this point is 1, 0, 1. It would be at 1, 0. The graph that you see here is 2 to the x power. And so the graph that we're graphing will be the log base 2 of x. So like here, this point is the point 1, 2. So it would become 2, 1. That'd be this point right here. Right here, I've got 2, 4. That would be 4, 2 over here. And then it kind of goes off of the graph. This point right here is like -1, 1/2. So that is going to be 1/2 -1 right here. This is probably like 1/4 right here. So I'd have 1/4 -2. And then it starts to get difficult to see what's happening here. But those points are going to get closer and closer and closer to that y-axis here. And this is going to be our graph of log base 2 of x.
What is the line?
That is just the line y equals x. So when you have inverses, you can reflect it over that line. So if we like folded this in half on that line, our two sides should match up here. A few things to note about here. Our exponential had a horizontal asymptote. Our log has a vertical asymptote there. Okay, this also, like, I have a pretty good picture of what exponential growth and decay looks like in my head. When I see it, I can think of what the graph looks like. Logs are harder for me to think of, but if I think of just flipping that exponential, it helps me see what I'm talking about. So, the exponential function, h of x equals a to the x, contains the points 2, 3, and 6, 27. Find the average rate of change of y equals log base a of x over the interval from 3 to 27. So here's throwing in like several things that we have done. Okay. This would be calculator inactive. So doing a regression and finding the equation is not an option. You would have to do it by hand, which again would not be the easiest necessarily to do. But this one can be done pretty easily. Because if my original function was h of x equals a to the x, and I'm talking about y equals log base a to the x, what would be true about those two functions right there? They're inverses of each other. And so if they are inverses, what's going to happen to all the points that were on the original function? They get flipped, right? So on log base a of x, I would have the points 3, 2, and this one right here would be, 27, 6. Because the points that they gave you came from the exponential. And so if I want average rate of change, when I see average rate of change, what's that telling us to do? That's slope, which is y2 minus y1 over x2 minus x1. And we want to use these new points. So that'd be 6 minus 2 over 27 minus 3, which would give us 4 over 24, which could reduce to 1/6 there, and that would be our answer for this problem. Okay, questions? That's the last one, right? Okay. On Canvas, I have it posted, so we'll just save some paper today, and it's about time to go. I realize you're probably not going to have time to get you can get your computer out and start if you want, but we probably don't have much time. I'll let you guys turn in Monday. Let's see. Or if you don't like weekend homework, it's due tomorrow. How about that? Then and no weekend homework if we do that. Thank you. Exactly. All right. So it is on Canvas right here. Just click on it. Open it up. It doesn't have a separate one with the answer key. Oh, I almost forgot. Test corrections. Please put them in the box for me. And if you will, if you already stapled, it's okay. But paper clip them instead of stapling them. If you already stapled, it's fine. I'll take them back apart. But I have to take them back apart for that. For this homework, just write it out on notebook paper. Or if you'd rather print it and do it on that, that's fine. But you can just write it out on notebook paper. And the answers are on the last page of that. I just checked it, so I do need to see it, but I don't have to keep it. Good. And if you'll get a paper clip and put those. Still do because I keep them, just so they're not like floating around out there. But even though I don't really need it, but if you'll put it there for me, that'd be great.